Hello everyone. Thank you for joining my presentation on 3D concrete printing freeform geometries with improved ductility and strength. I am Zeeshan Ahmed from Eindhoven University of Technology. For this research, I collaborated with Alessia Biffi, Lauri, Freek and Theo Salet from TU Eindhoven. Looking into the content of this presentation, I would start by discussing the state of the art relevant for this research, then moving on to discuss the research goal for this project, and finally the experiment. For the experiment, I will discuss a digital workflow and then two tests which is relevant for this, which is part of the experiment, that is developing double curve print bed, and second is printing a double curve panel. And the final test results are discussed at the end. Talking about 3D concrete printed projects, the number of projects around the world has increased significantly in the last 5 years. At TU Eindhoven, we have also been part of many of these valorization projects on 3D concrete printing. For example, the Pavilion in 2016, a 3D concrete printed bridge at Gamard in 2017, and there are two ongoing projects, which is another 3D concrete printed bridge, which is a 30-meter long bridge at Nijmegen, which has improved degree of freedom or improved geometrical freedom, and the second would be the project Milestone, which is the 3DCP housing project in Eindhoven. Talking about state of the art, I would discuss two topics. One would be on improving design freedoms, and second would be on developing reinforcement strategies which are relevant for this research project. Talking about improving design freedom, there are two projects which I would discuss. One is on using infill material as a support material for printing, and the second is 3D concrete printing on a double curve print bed. And in terms of reinforcement strategies, I would discuss metal cable as a reinforcement strategies, and second is how to introduce fibers into the printed concrete to improve the ductility of the printed structures. Talking about the first project, which is 3D concrete printing with supporting material, we started this project using sand as a supporting material. But sand having a high density, we realized that we wanted a material which has little less density or less weight to use as an infill material, for which we used lever grains, which are lightweight aggregates which is used for making lightweight concrete. And these lever grains have a density of around 170 kgs per meter cube. For the test, we started this test by printing it in an enclosed box, and simultaneously during the printing process, the lever grains were added during the process. And this showed significant proof of concept, and as in like the project was a success. So for which the next step was to check what is the degree of freedom which we can achieve with this process. For which the second test we checked the maximum angle of inclination, and during this test itself we realized the best angle of inclination or the maximum angle of inclination which we should achieve or which we should limit with during this process is around 38 to 35 degrees. And to make this process more efficient, we've also tested this process without an enclosing box. Moving on to the second project, which is 3D concrete printing on a double curve print bed. This project was in collaboration with TU Delft to develop a 3D printed shell structure, for which the outer mold of the shells or the panels were printed using the 3D concrete printer, and the shells were filled with concrete. And once these panels dried up, the shells were assembled using a temporary support. Moving on, the third project is on introducing reinforcement into the printed concrete, for which a special device called reinforcement entrainment device, in short RED, was developed, for which special nozzles needed to be prepared, which has a backflow extrusion, and this backflow extrusion accommodate for the entrainment of these cables. This entire system was tested and with various tests like the tensile test and compression test to check the validity of the system. To know more about the test results, please refer to the reference given below. The final test is on introducing fibers for improving ductility for printed concrete, for which a fiber reinforcement entrainment device was developed. The goal of this device is to introduce fibers into the printed concrete, and this is done by this device is into two parts. First is a fiber suction cum blower device, where the fibers are first added manually into the fiber bucket, and through the suction system, the fibers are transported into the mixing chamber of the fret system. In the mixing chamber, the concrete from the concrete pump is gets mixed using a motor and a mixing blade, and finally using another motor which is attached to an Archimedes screw, the final pumping of the concrete is done, where the concrete comes out of a nozzle. To look into the working of this fret system is shown in the video to the left, and this fret system was tried out with different types of fibers, both metallic and non-metallic fibers. However, the maximum dimension for the fibers were limited to 30 millimeters, because beyond that, these longer fibers sort of didn't work. It got clogged into the system itself. So for this research, glass fibers were used, which has a dimension of about 25 millimeters. So once the printing process is done, samples were prepared, and as you can see in the figure, you can clearly see the fibers into the samples. These samples, once they were prepared, they were tested with CMOT test, and comparing the test results of plain concrete and the samples with glass fibers, you can see significant development or significant improvement into the ductility of the samples. The more details of this test results could be referred to in the reference given below. Coming to the research goal for this project, the main research goal for this project was to develop a proof of concept for all these 4 projects discussed earlier. So for which we wanted to design an arbitrary shape to print a free-form object with improved strength and ductility, for which the experiment, as discussed earlier, is divided into 2 parts. The first part is of printing a double curve print bed on which the double curve panel will be printed. The double curve print bed was done using the infill material, using the red system for reinforcing the print bed, and the second is for the print bed, the fibers were introduced using the fret system. Talking about the digital workflow, a script was developed using Grasshopper 3D. The aim of the script was to consider design requirements of the panel as well as the considerations of the robot or the 3D printer itself. The panel geometry was deduced out of a sphere, and it was considered mostly in the sense that what could be the maximum angle of inclination, and this angle of inclination was kept as 20 degrees to keep it maximum, and this is from the reference, or this is from the recommendation from the project on printing on temporary structures. Moving on, the outline of this panel was used to create the surface of the print bed, and finally the boundary surface was created by using a mesh. Finally, from the mesh, the print bed geometry was developed. Finally, to make the print bed, this print bed was tessellated into 4 parts, and each of these parts were rotated 90 degrees before making the print parts for this printing process. Simultaneously, an internal woven pattern for the panel was also designed or developed to give more internal structure for the panel, and finally, both the panel and the print bed was checked to ensure the panel and the print bed has the same curvature. Once the print parts were achieved, the printing of the elements were done using the reinforcement and training device, or the red system, and you can clearly see from the figure where the position of the reinforcement cable is placed. So the reinforcement cable is at the middle or the center of the filament. And once all these elements were printed, it was finally assembled. During the assembly process, to avoid any kind of anomalies, an additional sheet of styrofoam was added to it to make the printing surface more smooth, and to avoid the panel sticking to the print bed, an additional plastic was attached to it. For printing of the panel was done using the fret system, and for this project the nozzle output was reduced considering the scale of the panel. And during the printing process, as you can see from this figure, that some of the points of the woven pattern were not attached clearly, for which it was corrected by increasing the overlap between the printed filaments, and the secondly by playing with the extrusion rate. Finally, you can see the printed panels which was developed during this project. So talking about the discussion or the learning curve, a 6-axis industrial robotic arm will provide better print quality to it due to its capability to follow the surface of the print bed. However, this process is limited because even if we increase the number of layers, at some point it will topple over. So this process is quite limited to making panels. The second is combining the technique of printing with infill support, and the red system shows the capability of improving design freedom with increasing tensile capacity for the printed objects. The process of adding the infill material during the printing needs to be automated, and its limitations needs to be further studied. The fret system showed promising results. However, further R&D is required to increase its capability to introduce more fiber typologies. Finally, coming to the final discussion, which is combining the fret system to make double curved panels with improved ductility gives opportunity for this application in building facade designs as well. With this, I conclude the presentation. Thank you for your attention.